Welcome to Once Upon a Geologic Time in the Raton Basin. My name is John Holbrook and I'm a professor of sedimentology at Texas Christian University. And I am a researcher. I study sedimentology and I have students who study sedimentology with me. And together we have been tackling the Raton Basin, trying to understand the nature of how the Raton Basin filled. We have many findings to share. I had 4 graduate students, a series of undergraduate students who did theses in this basin, and we're going to talk a little bit about what we learned. And the story is going to be about how vast coal swamps formed, how the land that filled the basin was about big distributed fluvial fans and coming in and filling in large coal swamps, and about times when dinosaurs once roamed the earth, then great rock hit the earth, and then suddenly they didn't. So we're going to walk through the story of the Raton Basin, talking about it piece by piece. So walk with me through this journey and we're going to tell the story of once upon a time in the Raton Basin. So the story of the Raton Basin, it starts here. We're standing on Simpson's Rest overlooking the town of Trinidad, and we're standing on the Trinidad sandstone. Probably the only formation around that actually has a big sign that says Trinidad labeling it. And so this formation was recording the beaches and the deltas, the shorelines that followed the western interior out, when once upon a time this was a vast seaway. The shorelines build out, the beaches build out, they leave these stacks of sand or the Trinidad, and finally, when the sea is pulled out, this becomes a vast area of fluvial systems and river systems, feeding beaches much further down dip, in the time that's leading up to the end of the Cretaceous, when T-Rex roamed the earth. Then, these mountains over here, the Sangre de Cristos, start to pop up somewhere towards the end of the Cretaceous, and they start to load this area. They start to push this area down, and they make what we call the Raton Basin, which this is the eastern edge of it. The mountains over there are the western edge of it, and the Raton Basin is all the stuff you see in between. This large bowed down region that started to pile up sediments that built up and filled the basin and make what we call the Raton Formation. So let's take a moment and talk about the formations that fill the Raton Basin. To begin with, we start in the Cretaceous, where we have the regression of the Western Interior Sea, and the Pierce Shale was the open ocean clays, which were regressed by the Trinidad Sandstone and the Vermejo Formation on top. Shortly after that, the Raton Basin starts forming proper, and we start subsiding the basin and building this big thick Raton Formation. So it starts at the very, very last 10 minutes of the Cretaceous. And so the lowest part of the Raton Basin, down in the lower coal zone, includes the Cretaceous Tertiary boundary, where we go from Cretaceous or Mesozoic time into the Tertiary, Paleogene time. And so once we start at the end of the KT boundary, we leave the lower coal zone and we start into the barren zone. The distinction between these two is relatively simple. The lower coal zone has coal, and this was a part of the section that was mined and attracted the miners. The barren zone is called the barren zone simply because it is very, very low in coal productivity. Little thin beds of it here and there, but not a lot. Then after the barren series ends, we move into the upper coal zone. This is a big, thick zone that records much of the Paleocene, and it's recording thick coal deposits like the king coal and so forth, which are major targets for mining. Somewhere at the end of the lower coal zone, this basin starts to fill in, though, and we have a collection of clastic wedge deposits coming across called the Poison Canyon Formation. Sandstones and conglomerates that fill across the basin and mark the demise and filling of the Raton Basin. We're at the Cretaceous Tertiary boundary, sometimes called the Cretaceous Paleocene boundary, but this is where the dinosaurs go extinct. And it just so happens to be right at the boundary between the lower coal member and the barren series of the Raton Formation. So thinking back on this, Below my feet is the lower coal zone. Above me is the barren series. This is an old miner's term. It was called the barren series because it doesn't have coal. Obviously, the lower coal zone has coal. So plenty of coal down in here, plenty of discussion about where the coal comes from, but we're in sort of a swampy world down below my feet, full of marshes and lakes and coal swamps, and then boom, all of a sudden, we're in an area that's dominated by upland river systems and fluvial systems and lots of river deposits, and the coal is largely gone, and the swamps that made them and the large lake systems that went with them are gone with it. And what happens to happen here is this: the Cretaceous Tertiary boundary. This is the fallout layer from the impact that takes out the dinosaurs. If you were over the size of a dog, you probably bit the dust at the end of the Cretaceous period, because you were faced with a massive nuclear winter. With the impact that makes this fallout layer that is the Cretaceous Tertiary boundary, it's an impact. A large mass of rock hits us from outer space. It doesn't have to be that big. It was only a few kilometers across, we figure. But that said, it made a crater over 100 kilometers across. And it threw up a cloud of dust that spread over the northern hemisphere and pretty much blocked out the sun over much of the world for a long period of time, creating very, very cold and very, very difficult conditions. This is going to be the upper coal member. It looks a lot like the lower coal member, and what's important about them, they're full of coal. So today we are at the king coal outcrop, obviously because that is one whopping layer of coal. That's 2 meters of coal, something the Raton Basin is famous for: big, thick coals that formed in big swampy environments. So let's talk about those swampy environments and what they actually look like. We're going to start down here in the least swampy thing we've got. This is the base of this section. So what we have here is a very soily type material. So what's pretty cool about this one is all of these pieces down in here, they have loads of little plant fragments in them. Lots of little pieces, little teeny pieces of leaves and sticks and twigs, and sometimes a little shiny bit of organic matter. But the other thing that these things also have is a lot of little shiny surfaces, like this one. See if I can catch it in the light for you just right. But they're slick-sided surfaces, like this one here, where the clays are shrinking and swelling. So plant roots, shrinks and swells. This is a soil. This would have been your classic swampy, wet, kind of shrink, swell, clay-rich soil that you'd never want to build a house on. As time goes by, we build up this soil, and finally we have this splay come in here, which this is just an example of many splays in this particular unit, but it's a little sandy sheet that's washed in across this soil. But what's really cool about this one, look at all these big roots. And some of these are a little coaly, and so these are going to have been trees that have established in here at one point in time, late in the age of this soil, to make this soily layer that's all rooted that came in right before here. So now we're finally up into the coal itself. This is the king coal. It's the base of it. So a few cool things about this coal. First off, we're going to take a chunk of it here, bust it up. And the first thing that you notice about this coal is it's really shiny. And when we say it's shiny, it's not just shiny in spots, it's shiny in little patches and so forth, with dull patches in between. The shiny parts of the coal would be what we call vitrinite. Vitrinite is made from wood. So this would have once upon a time been pieces of wood, pieces of trees making the shiny. The dull parts of the coal would have been things like leaves, spores, fungus, all the other stuff that makes up the organic litter in the swamp. So this would have been a very woody swamp. The compaction ratio of coal is about 10 to 1. So about 90% of this, when you saw it as peat, would have been water. And now it's pressed down and it cooked and it pressed down to peat. Then it actually had to heat up and cook to coal. You lost about 50% more. So for a foot of this coal, you'd have had like 20 foot of peat sum total to make it up. The clays don't compress as much, so to really get one of these clean coals, you had almost no sediment in it. We're still on the Valdez outcrop. We're just a little bit further towards the mountains on the Valdez outcrop, just a little bit up the road, and I'm standing right now on the king coal. So it's the same coal layer we were standing on before. This is the king coal. So it's largely a woody kind of swamp that was growing around in this area. Lots of shiny coal, and on top of it though, what you'll see at this point is some stuff we didn't see down before. This is actually a bunch of sands and muds and shales that all were here that are gone over there. These fluvial deposits right in here, these river deposits, record a river valley. They cut down through all this. This stuff has been cut out further down the outcrop. And up in here, it's present. And so looking at this stuff that's above the coal, what do we get out of it? Well, first off, a lot of cool features in it. First off, if you look at it real close, it's all layered, all nicely layered. That wasn't the case with the stuff I dug down below. The stuff that I dug up below was all stirred up by plant roots and so forth and soil processes. Well, if you look at this stuff in a normal situation where it's not above ground and it's not exposed, plants don't like living in here. After the water gets about a foot or two deep, the trees don't really grow so well. Also, there's not a normal fauna in most modern systems. So not in fresh water. So not a lot of things like to burrow around in that. That means that you don't get the stirring if it's underwater. This was a lake. So this was a lake. It's preserving the original layering of the sediment, and it's a common theme around here. You went from a situation where it was kind of lakey, kind of swampy. Here's a coal, and then a lake above it. The coals very often are just sort of swampy, woody zones inside of what would otherwise have been a lake. And so it's gone from lake to coal to lake to coal. Happens all the time in these two units. Above the lake deposits, what's cutting it out here is river deposits. This is a set of river deposits slicing down through them, cutting them out. The river has started from up there, well above these deposits, and cut down through them all the way down to the coal. And once they did, they made a valley. So this would have been high ground over there. This would have been the bottom of the valley. In each one of these fluvial deposits filling the valley, we can see this. That is a bar surface. These surfaces I'm looking at in here, they all dip down towards me and they lap out down here. They lap down to here. This would have been something like a point bar in a river, where the river would have been building the bar out into the channel towards me, making these surfaces, recording accretion of the bar as it builds this way, lapping down onto this surface where the bottom of the channel would have been. So given the size of these things here, this river would have been 6 or 8 feet deep. Down below it, there's another layer of these. So down below it, it's cutting into another channel fill that's down below. And above this, you can see the bar kind of ends up there and laps up and hits the top. And it ends up lapping up against those channel deposits over there, which is yet another layer of channels. So there's at least 1, 2, 3 layers of channels in this valley fill. That's because after the valley was cut, later when the water level rose, the channels are graded, filled up, filled the valley, finally filled it over the top, and then way past that, somewhere along the line, we started this whole cycle again, and another flooding over the top, and another coal starts to form over the top of this valley. Cokedale is located about 20 miles northwest of Trinidad. Here about 300 coke ovens remain just to the west of Highway 12, just outside of Cokedale proper. These are the largest surviving collection of coke ovens in the state. So initially Cokedale was a tent colony back in 1899, but it evolved into a little bit more of an operation with the American Smelting and Refining Company. By 1906, they were making coke. So coke is a process that takes coal and heats it to high temperatures, around 2,000 degrees, and about 6 tons would go into an oven. And coke is basically the coal equivalent of charcoal. Heat it really hot in low oxygen, and it makes a clinker that is going to burn much, much hotter when you actually try to burn it later. So you use coke to make steel and get those really high temperatures you need for smelting. What would a river have looked like in the Barren Series in the Raton Formation back in just at the end of the Cretaceous and the beginning of the Paleocene, starting in the Tertiary when we're depositing the Barren Series? Well, picture over here rivers coming out of a newly born mountains in the Laramide orogeny. The nascent Sangre de Cristos are popping up and they're building up. Storms are coming in, they hit the mountains, they wash off here making these big fans. The rivers that are coming through here are gushing. And by gushing, means they are white water type rivers. They're leaving these very unique deposits. Watch this pattern here, that nice wave. See how it goes up and down and over, like that. That's called an antidune. That's a symmetrical antidune. What that's telling you is you are near upper flow regime conditions. You're where the velocity forces of the river are starting to equal to exceed the forces of gravity of the river. And so that means that you're making these large standing waves that would have been whitewater type channels. These are huge. Picture yourself going down here on a river raft, riding over that wave. It would have been a good time, class 2, class 3 rapids. And then this one's not alone. Look right here. Here's another one. Here's a big tall one right here split across this crack. And then up above it, yet another one. This whole thing is filling up with these upper flow regime type structures, telling you that you're dealing with massive flood outs, big bursts of flood that come and flush through the system and go. And at the mouth of them, they take all this sediment and sand and flush it out into these big sheets. And that's what makes our terminal splays. Let's go down here and now look a little closer up at some of these terminal splays. We're going to walk down to that rubble pile right down in here just a little further down the outcrop and look at some of these terminal splays. You can see they're really extensive. We were down here below looking at the main river channel cut into all these terminal splays and cut down to this coal that marked the beginnings of the floodplain, the end of the quiet period, and the onslaught of the sediment rushing in here with the terminal splays. I'm standing on the coal a little further down dip. These sheets that make these terminal splays are extensive. We got about 8 or so of them stacked up in here one at a time. One sheet, another sheet, another sheet, all stacked up, very often with a little bit of mud in between them like this, recording the quiet times between the splay sheets. So the splays themselves record the end of the river. The river has lost its integrity, it's lost its channelization, and all the sediment and the sand is just spraying out in a big fan shape, a big splay shape, out onto the floodplain. And it's making these sheets, all these different terminal splay sheets. So let's look real close at what these splay sheets look like. So inside these splay sheets, you get a lot of little ripples, but mostly you get upper plane bed, these little thin layers of sand that are recording where this is flowing out as a thin sheet of water. Well, thin, might have been knee deep, but it was moving fast, moving at a hurry. And it was making these sheets of parallel laminated sands underneath. And periodically, well, after it was all said and done, a few little roots. So every now and then you'll see a little hole here where there's a root or a burrow or something came in here, because this is land. After this splay is done, it goes back to being floodplain until the next one comes in. So things live here. So these individual parallel laminated sheets, though, often have undulation. So over here, we can actually see this one. It's got sort of a hump to it. This is familiar. This is a little version of the big antidune that we saw down there. And then somewhere over here, if you look real close at this particular sheet, all these parallel laminations are at a slight dip to sort of flat. There's a little undulation to them. This is upper flow regime deposition. The water's moving fast as flood out sheets as it goes out here and spreads the water out and the sediment beneath into these big sheet flows of water with these sheet flows of sand deposited underneath. And then one after another, every few years, here comes another sheet, until finally it's all over up top, and we go back to floodplain again, and things go quiet for a little while until you get way up there at the top, and then that's the next bunch of these coming in. These form big, huge lobes of splay sheets that come in periodically, build over here, build out, then they build over there. We saw these in Argentina. We actually went down to try to find a modern analog of these, because one of the things that drew our curiosity is these sheets. We wanted to understand them in the Raton Basin. So we went to Argentina to find their modern analog. And in Argentina, what we found was the one place in the world where we could find humid, tropical kind of versions of these terminal splays, where rivers are coming out of the Andes, the Bermejo, the Rio Seco, and they're pouring out of the Andes out onto the floodplain. They end in the flats, and the Rio Seco just spreads out these big sheets of sand, making these big lobes. And these things will be a couple kilometers across, half a kilometer across, a kilometer long. Depends on the size of the flood, but they're hundreds of meters across, hundreds of meters long, as big fans formed in single flood events. And that's what these sheets are recording, that torrent that comes through in these massive floods that ends and floods out these big sheets, laying these terminal splay fans like we saw in Argentina. We have leaves, abundant leaves, several leaves of various things, birch type plants and so forth. Most of the terminal splays that are discussed in the modern are in arid desert environments where rivers just simply flow out into the vast flats of the dry land deserts and pretty much soak into the ground and dry up. What's special about these in the Raton, this was not the case. This was a humid, tropical kind of place. It had lots of trees growing in it. And when these splays would come in, they would bury these trees. So this is an upright standing impression of a tree. There's the various little rootlets that formed where this tree once stood, sending down its roots into the ground below. When the splay came in, it buried the tree. And the tree has stood there buried by this. We have seen in Argentina, in the humid areas in the Tucumán-Oran jungle area, we have seen where whole forests are buried. Trees are standing as much as 2 meters high, completely buried with the surrounding sediment. Thus is the case that it was common that trees were getting buried by these splays because there were forests there when these splays came in. It was a wet, humid land. Once again, we're at Simpson's Rest, overlooking the Raton Basin. We've talked about how the Raton Basin formed. We've talked about how it filled. We've talked about all the research that we've done here with Texas Christian University, trying to understand how the basin filled. And we've talked about how it ties into the understanding of the history of this region and why so many things about the geology of this area is important to the people who live here. So with that, I'd say see you again once upon a geologic time.